This is a quick video showing one run of the current version of the SLAM code. It's labeled with its date 2020-08-29 because I'm doing this on August 29th of 2020. The code is written in Mathematica, so in order to get started I need to have some files available. Here's the file that has the SLAM code in it, the Mathematica notebook. I've got an Excel spreadsheet that is the input earthquake data file. I have a digital elevation model, and it's an ASCII file. Its identification is .dat, and I've got an output file folder called output files, cleverly enough. Inside of this Mathematica notebook, I have to supply some information. So the first bit of information is to tell the software where to find the input data file. So here's the path name. Okay, and if I am unsure of the path name, at least in my Macintosh version of this, I can just sort of drag through the existing path name between the square brackets, and let's just vaporize that. I can come up to Insert, down to File Path, and then I can navigate my way to the file that I want. So it's called Input Earthquake Data File. I choose that, and notice it inserts the correct path name. Now I can use this for any other input data that I've got. It says specify which record in the input data file will be acted upon. So the next blue box has another decision point, and so I'm going to take a look at my earthquake data file. Now I've already run some earthquakes earlier this morning, so I did the 1966 one, the 1977 one, and now I want to do an earthquake from 1983. It occurred on July 3rd at 15 hours, 8 minutes, 20 seconds, and so forth. So that's the one I want. It's record number 4 in this Excel data set. So I'm going to specify counter is 4, so I can pick up record number 4. Let me see. Here is the digital elevation model. Okay, so I've got that set from previous runs. I need to put in the geographic box that I'm working on and the zone meridian, which for Tahoe work is going to be -123 or 123 degrees west longitude. Okay, let me see. Here's a bit of code that I don't need because I just moved it up there. So let's get rid of that and save the new code. Okay, so the last thing I need to do is come down here and change the name of the output file. Now the previous run I did was on an earthquake from 1977. The one that I'm working on now is from 1983, so I'm going to make that change in each of these output records for my own convenience. And these records eventually will end up in that output file that I showed you earlier. Okay, without any further ado, let's fire up this puppy and get it working for us. So we go to the evaluation menu and choose Evaluate Notebook. And it's going to run its way through this notebook. You can see that it's already working its way down through the various tasks that I have set for it. It takes about 2 minutes and 2.7 minutes or so to run through at the moment. So we're going to come back as soon as it's finished, and what we're going to do is take a look at the pictures that it's going to make for us. Okay, it has done its computation, and here's the output. Just the way this thing is set up at the moment, it outputs a hillshade map based on the digital elevation model that we fed it, which is called North Tahoe vthin.dat. It computes the boundaries of the seismolineament. This is sort of a complicated thing that looks like I dropped some spaghetti, but what I pay attention to is the outermost line, okay, outermost curve, if you will, on one side, the outermost curve on the other side, and that defines the outer boundaries of the seismolineament. And running along here is the ground trace of the nodal plane that goes right through the middle of the focus of the earthquake and makes its way up to the ground surface, given the dip angle and dip azimuth that was supplied in the nodal plane data. It also has a little square where the epicenter of the earthquake would plot. The third is that little series of lines, curves, superimposed upon the hillshade image. The export data includes the original hillshade image, that little line map, and the line map sitting on top of the hillshade image. These things are now all safely over in the output files. So here's map 1, map 2, map 3. And what I'm going to do, just for organization's sake, is I'm going to create a new folder in this file, and I'm going to give it a name that identifies the earthquake I just worked on. So I'm going to call it 1983 07 03 15 08 20 39.412 is what it should be. Okay, so once I have all that stuff in, I'm going to grab a hold of these output data files and just stick it in that folder. Okay. And, you know, I'll just go back and make sure I've got this number right when I have a moment, but that's basically the workflow that I go with. And now I'm all set up to look at the next earthquake. And in order to do that efficiently, what I'm going to do is come up here, click on my window in Mathematica. I'm going to go to the cell, delete all output, because I've already saved the maps. I'm going to save the file, and now I'm right back to where I began. I can now come down here and advance the counter by 1 if I want to look at the next earthquake from 1992. And over the course of a little bit of time, I can get all of my earthquakes analyzed and produce these initial maps. They're produced on a fairly coarse digital elevation model, but then I can superimpose them on the finer grain model used with LiDAR data, and I can use Adobe Illustrator to do that. Okay, that's all for this topic.